So, executive summary of what we're trying to do here. Right? Also, to sort of frame our mind again of, why we're doing gluing in the big picture of things. So, when I say we want an analytic description of our moduli spaces, what I mean, most of all, so we'd like to describe we did describe the sort of smooth, well, not the smooth, we did describe the part of the moduli space that consists of smooth curves as zero set of a Fredholm operator, right, or Fredholm section. And now we'd like to do the same thing for the compactified space. Right? So we're going to have to deal with these broken and nodal curves. So the key here is to say Fredholm section. That's sort of the analytic description. Note that what I'm not saying is I don't need them transverse. Because in general they simply won't be transverse. Right? Anyways, we're thinking now about a situation in which maybe by wiggling with J, you can't get them transverse. Right? And also, we want to, in fact, really, so I'll usually write curly things for infinite dimensional spaces. So there's a Banach bundle, some section in it. So we actually do want to have directly the zero set sort of being locally embedded in the compactified space, not something where we have to still mod out by a large automorphism group. And that's because so describing the moduli space by zero sets modulo a group is really not going to give us the right kind of framework in which we could then abstractly perturb. And that's because in general we do not expect out equivariant transversality. Right. So the idea is quotient out first somehow, in the infinite dimensional setting, and then afterwards try and get transversality going. Yes, right. And what I'd like, right, so that's going to be, some zero set in here. And I'd like, that's a Banach manifold, and I'd like that zero set to be locally homeomorphic to something in the moduli space.
Oh, is it embedded?
Yes. Yeah. Not a... That's... Well, M bar does not sit in this big Banach manifold as a full set, right? It just locally we want to describe it this way.
So several Banach manifolds.
Right. This is all going to be locally, right? So we're sort of starting to kind of make some sort of atlas for our compactified moduli space that where each chart consists of a section in a bundle and a local homeo from the zero set into. Good. Okay. So, what have we done so far? And I'm just going to go through the Hamiltonian case now because that's what we'll talk about. So we described the broken and nodal curves near which we need this description as fiber product, and in this case it's a pretty silly fiber product. It's over a finite set. And we're going to make things even easier because we're going to look at a case where this is just a finite set of points, and so we're just going to do the description near an isolated broken curve. So we'll simplify to that. isolated and transverse. So a pair of transversely cut out Floer trajectories, right? So I imagine I have my I have my differential defined by these isolated trajectories, right? And then these pairs are exactly the stuff that I want to sort of count when I try to prove that d squared is 0. So that's really why we're interested in those. So yeah.
Can you repeat what happens when I have a cylinder approaches to that in terms of like how the energy distribution?
Yes. Well, so you're saying convergence?
Yeah.
Yes. Okay. Excellent. Good question. I was going to briefly review that too. Right. So, right. So how do these broken curves sit in my compactified moduli space? So that was our first goal that we did with the pre-gluing. We wanted to, give this compactified moduli space a, compact metric topology in which convergence to a broken curve is exactly the following. So I've actually taken even more things out of here. So convergence means, in this case, to just twice broken trajectory, that I have shifts, and that the shifted maps converge with all derivatives on all compact sets to the two components. So that by itself, is not a good sort of convergence. The limit is definitely not unique this way, right? Because you could take all kinds of shifts and they all converge sort of, to the same trajectory. So we want to make sure that there's only one way that, well, these will never be unique, but we want to make sure that the limit is unique. Right? And so the way to make that true is by asking that the energy is exactly the sum.
You also need
so,
the difference goes to infinity.
No, I don't need that. That's going to follow.
I don't think so, because what if you do the following? Imagine that the top cylinder U plus and U minus.
That's silly. Right, yes, sorry. Yes, right. Right, U plus and U minus could have the same energy, right? Yes. Good. Okay. Good. Right. Okay. So this difference, right? So that makes sure that I actually sort of, these compact sets really see different parts of my whole cylinder. So, right, and the fact that there's sort of no energy lost then is actually going to strengthen this convergence a lot. It's also going to prove that sort of things connect. So this is going to tell me also that U plus and minus need to have sort of the same limit at the other ends. It's going to tell me that it actually needs to come from gamma plus and gamma minus. And all of that has to do with some argument that says, well, if it didn't, then let me go fairly far down this convergence here. I'm really close to a different periodic orbit. But now the U nus actually still have to go to gamma plus or gamma minus, or they have to match up, and that takes some energy. Right? But I don't have extra energy, so So this is sort of the minimal notion of convergence that implies more things.
And if you were just doing ordinary Morse theory, the same definition of convergence would give you the right compactified moduli space?
Yes.
Yes.
Yeah. Exercise. Another thing here is, I said C infinity log. I don't actually need I can replace this by any W1, any WKP log, in fact. And that's because these are all holomorphic curves, so I can use elliptic estimates. So, well, from C infinity log, of course I get any Sobolev convergence. And if I have strong enough Sobolev convergence, I can use all my elliptic estimates to get all other derivatives to converge. So here I just need to be sort of above the critical level where sort of the bootstrapping works. So I think I just need Kp bigger than 2, which is a nice thing anyways, because I might want things to be continuous. So, and we're going to use that later on to prove convergence. Okay.
And so Nate's comment about if the energies are equal, you would need this condition on the S pluses, because this converging thing U might just decide to take some portion of S plus, some portion of S minus. It doesn't necessarily split U plus and U minus into two parts of the cylinder.
I think the problem is you might have just accidentally looked at the same map with both.
Right. Yeah, I mean, the silly thing is, let's say you knew if I don't. So usually the way to find these is also to sort of first not shift at all and just see what you knew does. Yeah? And you're going to find that it's going to converge to some Hamiltonian Floer trajectory. It's going to be one of these two, right? So let's say it's U minus. And then I could be silly and set both of these S's equal to 0. And then, of course, both converge, but I would get U plus equal to U minus. And if now by some miracle the energy of U minus is exactly half of the energy here, I would have that identity, right? So this condition here makes sure that these two energies here really come sort of from different parts of U nu, right, or from diverging parts. Of the cylinder, right? So this, together with this energy identity, says that there are parts of energy that on this cylinder, on the U nu cylinder, sort of diverge apart. So if you look at the sort of, no, there's no center of mass. There's blobs of energy, and you'll find very little energy somewhere in between. And that's where the very little energy is. That's where you go to the other periodic orbit.
I'm assuming it doesn't matter, but should we also be assuming that both of those energies are positive and that this is an
Oh goodness, yes. Yes. I mean, it does. Oh, sorry. Yes, it does matter.
I mean, there's nothing wrong with the curve not breaking.
No, but I wanted to say in what way this converges here. Well, I guess. I mean, I drew U plus and U minus as non-constant maps, right? So U plus and U minus should both be non-constant. Yeah, I mean that's sort of an important rule, If some rescaling gets you a constant sphere, that's not actually bubbling, and if some shifting gives you a constant Floer trajectory, that's not actually breaking, because that's just silly. Nothing bad happened. All right. Good. So now that we know what this broken nodal curves look like, we'd like to, really describe. So when I say, right, so we want an analytic description of our moduli space, of the compactified one, near the broken and nodal curves. And the way we're going to do this is we're going to sort of review the pre-gluing briefly, that interpolates these two Hamiltonian trajectories, gives you a map from the cylinder with small d bar, and then we're going to run a Newton iteration to get an actual solution. So what this is going to give us is a gluing map So that's good because, well, goal 3 is going to say actually we'd like the gluing map to be a local homeomorphism. Right? And then this here, right, so let's say we've already done our analytic description of the moduli space of non-broken curves. Right? So then we're just adding this fiber product here, so that also gets as a Fredholm description. Right? And so at a gluing parameter here, we'd have a nice Fredholm description on this side. Right? And if our gluing is a local homeo, then we're exactly getting a Fredholm description near the broken curves. So that's the reason for this master plan. Right? Good. So, good. Main tool is going to be this Newton iteration. Well, the result that you get from Newton iteration. So, let me try to remind you what's happened in Newton iteration. So you're on linear spaces. You're going to, well, it's a little silly. There's an x0 and x1 that are both going to be 0 in the application. So there's some open set on which we have a continuously differentiable function whose differential at this one point is surjective. So it looks like a sort of transverse, well, not necessarily 0, but, oh, actually, there's a, oh, no, right, no, f of, right, this is not a 0, you know, if it was a 0 of f, then this would be a transverse intersection, but, you know, we're guessing that there's a nearby transverse intersection. So not just surjective, I'd like it to have a bounded inverse or a bounded right inverse if it has kernel. And then I'm going to fix some constants. So yeah, I need a small ball around my initial point on which I'm going to allow myself to try and solve. I want to keep track of how fast the derivatives change nearby. Right? So there's going to be some estimate here just because f is c1, but I'm going to call this 1 over 2c. And I am also going to want the right inverse to be bounded. And so that c here is the same c as that c. So this means here, right, I can't do anything about the right inverse. This means I'm making the derivatives pretty close to each other. Good. And then I'm starting with something that's almost a solution, x1. So, yeah. And I'd like it to be very close to x0, so I have some space to wiggle on it. So almost the solution here is quantified in terms of this delta and the c. And this is exactly the quantity that you need to get the Newton iteration to work. Because then what Newton iteration does, let's see. Right, so I start at x1. It's not a 0. But I look at the derivative here, it's non-zero, so if I follow it, by a straight line, it's going to hit 0 someplace. So that's the next approximate 0. I'm going to call that x2. Right, and solving this equation here to find x2 is exactly what requires this right inverse. And then at the next function value, again, I take the derivative, see where that gets me. In this case, it already gets me pretty close to the actual 0. So, the theorem here says that, if there's very little curvature in my function and I'm already very close to 0, then in fact there is a unique transverse 0 near in my little neighborhood here, and this iteration is going to converge there. So that's the nearby solution. Well, I'm solving in this image of the right inverse, so I've picked a complement of the kernel. And I'm going to be close. And in fact, the new solution here is going to be the closer to the initial point, the smaller the initial sort of error was. Question.
Is the guarantee that the intersection is transverse going to come from the bounds of the derivative, or?
Yes. Yeah, I believe, right. So yeah, right. So here you have a right inverse that has something with C, right? And here you're asking the to vary with at most 1/2C. So I think, right, if you go through this, so these together should imply that df of x also has right inverse. Qx, that is sort of not too far away from Q, the right inverse at x0. In this little neighborhood. So yeah, and that, that's what also guarantees the transversality of that intersection.
So in the context of Floer gluing, so I'm thinking of x0 as being my approximate solution. So
x1.
Okay.
Yeah.
What am I thinking of x0 as being?
The same thing.
I see.
We'll get there.
Okay.
Yeah. So eventually both of them are going to be. Yeah. This is the general form that sometimes is useful, and that's the one that's in McDuff-Solomon. Right. Do I want to? Well, since you. No, we're going to have to review pre-gluing anyway. So let me sort of tell you the end of the story first, and then we'll actually go in and do the Newton iteration. So finding unique zeros is only going to sort of make this map. So it's going to give us a gluing map. You then still have to be careful that to translate the uniqueness from the Newton iteration to uniqueness of the gluing map in injectivity. You also want local surjectivity. So that's something like saying if I have a sequence rho of something where the gluing parameter goes to 0, where that something here is a broken curve, then I'd like this to actually go to that broken curve. Well, that's one thing. So I actually go to the broken curve, and if I have something that's close to the broken curve, then I would like it to actually be in the image of my gluing map. That's two statements here, right? This is the better. The second is the better notion of local surjectivity, I guess. The first one. I should maybe call compactness. Yeah.
This might have been covered in a previous
Yeah.
lecture, in which case just tell me to watch the thing when
Well,
it goes up.
yeah.
But in the previous thing, you had this local surgeon, or this bounded right inverse.
Right.
And this gave sort of a transversality sort of near the gluing area.
Yeah.
Does that mean that kind of when we do this gluing procedure, we need to start with everything being transverse, and do we need?
Yes.
Or do we always expect to
Well.
end with transversality?
Okay.
It
Yeah.
seems
No.
like
This is okay. This is deeper than what I wanted to talk about right now. I wanted to. So my master plan is to first show you gluing in a transverse case, and there you start with a pair of transverse curves, and then yes, automatically the glued one is also going to get cut out transversely. Obviously, that's in general we're going to have to if we're going to want to sort of describe very singular moduli spaces, we're also going to have to deal with gluing of non-transversely cut out curves. And but the trick is to always get yourself into a situation where something is actually transverse. And the way to do that will be to just add some extra parameters to your Debar equation that that soup up the co-kernel. That's something called, I guess, stabilization. And so you have these local Fredholm descriptions there. You can always stabilize a Fredholm description by just adding an abstract extra space that covers the co-kernel. And so then you're going to you're not actually looking at gluing curves that are holomorphic, that are going to be holomorphic up to the stabilization. And then you want to glue, and you're going to get a description of sort of holomorphic things up to the gluing of stabilizations. And that's where bad stuff starts to happen with so yeah. But there is I think it's important to sort of see the basic, the simplest version of gluing first. So, yes, but that's right. I mean, for the experts, you always want to sort of have in the back of your mind as well, what would I do now if stuff wasn't transverse? All right. Good. So, however, now I would like to write. So now I'm going to assume for myself that everything is nicely transverse. And I want to argue quickly why this gluing map and this being a local homeomorphism actually proves for me what I want to prove in Hamiltonian Floer theory, namely that d squared is 0. Right. So let's see. Right, so in this case, right, so the broken curves are pairs in sort of zero-dimensional moduli spaces of connecting trajectories. And I've drawn the compactified moduli space here, sort of with a little wishful thinking, right? I'm hoping that that is going to be a one-manifold with boundary given by the broken one. So, and there might be several such. So, locally, now this gluing map is just going to map an interval 0 to epsilon, well, 2m bar. Well, right, if we prove that it's injective, then it's an embedding. And this local surjectivity tells me that the image of rho is in fact a neighborhood of the broken one. So, pictorially, Oops. Okay. Right, so each glued one here, so this is maybe rho of some epsilon I less than epsilon. Right. Each one of these is actually a point in my compactified moduli space, and what I'm saying here is that actually there's sort of a whole neighborhood of these. It's going to be open. That's the image of rho. So, and now I can run compactness again in my space of one-dimensional Floer trajectories. And my claim is that now m bar 1 minus the image of rho will be compact. Reason being, right? Let me look at a sequence in here. The kind of Gromov compactness that I should have proven is that sequences in here either converge to, a non-broken trajectory, or they converge to a broken trajectory. Only two possibilities. And if they converge to a broken trajectory, eventually they're going to have to be in this neighborhood of the broken one. However, I took that out. So it can only converge within the unbroken ones. So it could converge to this boundary point, but it's not going to converge there. And if everything was transverse, then this is going to be a compact one-manifold. So I could now do two things with this. I mean, this is really what people use, what strictly speaking, we prove. You could use this to produce, a compact one-manifold topology on the whole compactified modular space. Right? So. Right, simply by gluing rho, or the image of rho, to this compact one-manifold, you have some kind of smooth overlap maps. So that's an atlas. But we don't really need that, right? Because what we now also know is, well, the sum over the ends of this compact one manifold is 0. So the number of boundary points of this is 0. Well, and there's one boundary point for every connected component of the image of rho, right? So this is the same thing as number of connected components of image of rho, right? Because there's one boundary point for each of these. But, right, so where's my gluing map here? Right, my gluing parameters here were 0 epsilon, and so the connected components simply come from this fiber product. And those are the broken curves. Right? However, the broken trajectories are exactly the contributions to d squared. So, right, you don't necessarily need to actually, make a compact topology on your compactified moduli spaces if all you're trying to prove is that something is zero. So,
Excuse me?
good. Yeah.
So did we actually do this thing about considering m bar 1 minus the image of rho?
Did we do that?
Well, yeah, so...
Just now.
Right there, yeah.
Yes.
But did we need to do that? I mean, couldn't we have said that, based on the splitting argument, we now have the structure of a one-manifold with boundary on...
Right, that's
M bar 1.
on m bar 1. Right. We could have done that, yes. And then, yes. And then you have to talk about what the boundary components of this are.
Where the argument of compactness comes from elsewhere, you're saying?
Well, so
No,
here's
I mean,
actually, so I think the other way of saying this is I could have not done either of these. I could have said m bar 1, well, I could have said the one-dimensional moduli space without the broken trajectories is now a one-manifold full stop. It's a non-compact one-manifold. And I could then just quote a general classification result that says the number of ends of a one-manifold is sums to 0 with orientations. Right? And what rho for me does here is it identifies the ends with the broken trajectories.
Right.
Because for each end, there is exactly this embedding of this small interval that parameterizes the end. Right. Good. So that was the lowbrow application of gluing.
Sorry, so the fact that for each end you have a broken trajectory, is that Gromov compactness, or what are you
Yeah,
saying?
that's
Because you need to argue that
right.
such a
Rho is locally surjective, and it's right.
Because you've argued that if there's a broken trajectory a priori at that end, then you're fine. But I don't see how you've said that every end has.
Right.
Okay, good. So you need.
So that's well. There's actually this sort of. It's locally and globally. Right. So globally means exactly this, that if I have a map that's close to a broken trajectory, then it lies in the image of rho. And so I guess this argument here tells you that really, makes it more clear that you really need to prove these things. So mainly I'm listing these extra properties here to say that just making the gluing map is not the end of the story. There's some extra properties you have to check of your gluing map before it's actually good for anything.
But the proof of that is Gromov compactness for the cylinders.
Well, it's Gromov compactness and right. So Gromov compactness tells you that if it's close to broken trajectory, Gromov compactness tells you that it's compact up to convergence to broken trajectories.
Oh, I see.
Right. So the gluing map still needs to make sure that it actually hits everything that gets close to broken.
So are we going to prove that statement later on?
Maybe. Yeah, that's probably exactly the wrong thing to do is to just say these other properties are important and then to not discuss them. So I'll try to at least discuss them. They're usually doable. They're pretty fiddly, and sort of analytically, the main part really is this Newton iteration. But yeah. All right. Good. So now let's get ourselves into the setting of, actual Hamiltonian Floer theory. Right. So at this point, I need to. So I'm going to take a broken trajectory. Right now it's not important, but in a moment I'm going to assume that they're cut out transversely and index 1 mod r, so they're isolated solutions. And I'm translating my gluing parameters here into large numbers r e to the minus r. Okay. So from this, I sort of sketched how to make a neighborhood of things close to a neighborhood. Right. This is right. These are not quite holomorphic. They are holomorphic. So for gluing parameter 0, meaning when r sort of is secretly infinity, I should just get the broken one. Right? And for finite r's, I would like to get an unbroken trajectory. Equivalence classes here always, because I might be working mod r. Well, I am working mod r, right, to be rigorous. So now I need to tell you what this is, and I'm actually going to do the construction that Solomon does. There's many different ways of doing this pre-gluing. The important part is that, well, you pick two parameterizations. Yeah, I would center them maybe so that the center of energy is at 0, but it doesn't matter. You just pick them once and for all, and then you shift them apart. So there's one part here where you'd like, well, u minus of dot, what is that, plus r. That then means that whatever u minus did at 0, this shifted one is going to do that at minus r. So this energy maybe here gets moved over here. We're going to do the same thing here. U plus, except now I have a minus r here. So whatever happens in a large interval around 0 is now happening in a large interval around plus r. So, and then I'm going to take, let's see, what else does he want? Right, there's this interval between minus r over 2 and r over 2, where he makes things nice by simply setting his trajectory, or his pre-glued thing, equal to gamma. That's the broken one. So that's the limit. It's the positive limit of u minus and the negative limit of u plus.
So this is the non-continuous?
Well, right, and so we've done something wrong here, obviously, right? So we need to actually do something else. So in a small interval here of length 1, we're going to need to interpolate. And so here is a complete formula for W. So I'm going to be able to write it, so W at S and T, I'm going to be able to write as something in a geodesic neighborhood of this periodic orbit, of what? So now if I'm at this end here, I really only need to cut u minus off. So I'm going to write u minus first in that neighborhood, right? So u minus for what is this? R over 2. So u minus for up from R over 2 minus 1 up to infinity, I guess. So that's here. Okay. So I'm taking my R large enough so that this is very close to gamma. So then on that interval I can write U minus as exp of some section eta. And so now I'm simply going to take that section eta and cut it off with a beta here. Cut a function. And just so we have the same cutoff function always, should be a cutoff function. Send it at 0, and it just gets moved to minus R over 2 times eta. So that now needs to get shifted exactly the same way, with S plus R. Right, so where beta is something, let's see, that there's no graph for, so beta better be 1 when S is R over 2 minus 1, I guess? Or R over 2 plus 1. Oh, jeez. What's going on here? Oh, if S is... Right, if I'm 1 over here, right, for S1, right, I'm going to need beta equal to 1. And when S becomes minus R over 2, oh, Jesus, no, when S becomes 0, right, no. When S becomes minus R over 2 here, right, then I have beta at 0, so I'm 0 here. As usual, simple algebra is the hardest thing. So we can do this here, and we can do this interpolation there similar. So you're just going to have x gamma and then some other shift of beta, which in that case is S minus R over 2, and then some other, what do you call this, eta minus, and the analogous eta plus, where right, near the negative end here. So in this area, U plus is about, or is actually equal to exp gamma of eta plus. All right. So what happens, right, is at the ends I write this in terms of some sections in some vector bundle, because in that vector bundle I can then multiply with cutoff functions. And this is a particular nice way because you don't have to deal with interpolation. You just cut off, stay at the critical point, turn back on. You can do anything that really just ends up not mattering. Good.
So I'm a little confused. So to actually use, so this vector bundle that you're talking about is the normal bundle to gamma, right?
Not the normal bundle. So the eta plus minus are sort of sections of the pullback tangent bundle. TM. Right, so at every point of gamma I can go in any direction within M.
So such a parameterization only works if you're like near the times positive infinity or
right.
negative infinity.
Yes.
Okay, great. That's where this.
That's right. So that's why I need R large here. Okay. So I shift these guys far enough apart that in the area where I want to cut them off, they're close enough to the periodic orbit that I can. All right. Good. So, pre-gluing is done. So now let's see how we apply this. This is a restatement here of the Newton iteration. So let's see. What I want to solve here certainly is that.
Are we a part of being a holomorphic?
Are we what?
How small is this?
How small? Well, we'll get there. Better be very small, right? Well, let's look at this briefly here. Gamma is in fact holomorphic because we're looking at perturbed holomorphic curves with an H in there, right? So gamma is a steady state, is a constant solution of the Floer trajectories. U minus and U plus shifted are also solutions. So really the only places where d bar is not 0 is on these little interpolated intervals. And so you can guess, right, that you can get eta plus minus pretty small, and then you're just going to cut it off. So these things are very, very close to, the periodic orbit, so d bar should be very small. All right. So
aren't there contributions coming from how quickly eta grows? I mean,
well,
cutoff function isn't this? So if you're shrinking an interval, but
right, that's part of the. I mean, that's the reason that I always want the same beta. No matter what r.
Great. So it's a width one
that's the
always. It's
yeah.
not
Yeah.
Great.
Yeah. That's yeah.
R is getting bigger, so really.
Right. But so the cutoff function is just getting shifted. Its derivatives are always bounded.
Great.
So, yeah. Yeah. So this is a good thing. We're gonna, the crucial thing is that we're gonna apply this proposition for all sufficiently large r at the same time. So, and what we're gonna look at is essentially we'd like to, solve d bar equal to 0 near the pre-glued curve. So I'm going to look at d bar of exponential map at the pre-glued curve on something. Essentially. Okay, so, and this zeta is going to be now, a section in the pullback tangent bundle there, and it's going to be pretty small. So what this u here is going to be some delta ball, in some space of sections, say W1p of WR star TM. And then forget about x0, we're just going to look at it around 0. So 0 here is, that secretly is the point WR, so that's the pre-glued curve, except we're working with exponential map. So then, right, we're going to want to look at the differential, which is what we're going to make this the sort of linearized operator at WR of the d bar, the perturbed d bar operator. All right, and then taking some constants that hopefully fit with my right inverse, and I'm going to take an almost solution. My almost solution really philosophically is WR, but that corresponds to 0. So I'm going to start at 0, then this is not a condition here. 0 is equal to 0. But what I need is d bar at WR to be pretty small. And then I'm going to find a nearby solution. Maybe I should call that zeta. It's going to depend on the gluing parameter now, right? Because for every different gluing parameter, I'm starting I actually have a completely different problem here, right? So this is going to be FR. And this zeta R is now going to be a nearby solution. So f of x equal to 0 means nothing else but d bar jh of x wr zeta being equal to 0. And in our Hamiltonian Floer case, the bounded right inverse is actually also going to be not a left inverse. Sorry, I'm lying, right? So if you could imagine that, you know, if there's a multitude of broken curves nearby, you're going to expect a multitude of actual holomorphic curves nearby, and so it's not, you need to sort of fix which one you're going to get from which preglued curve, and that gets organized by asking things to be, you know, in the image of that right inverse.
So what was x1?
X1 is 0.
Oh,
Right, so in the abstract theory, we started with an almost solution, and here we're going to start with 0 being the almost solution. Right, so 0, right, 0 here means I'm putting in 0 here, so that's then just WR.
So for the right inverse, we should think of the adjoint, right?
You can think of whatever you want, yeah. This, you know, the adjoint is one way of constructing a right inverse explicitly. Right, and there's going to be another estimate here that's going to give us the, again, norm of the correction term will actually be bounded in terms of the not quite 0 of this, you know, preglued solution. So that's again the d bar jh wr. So, right, so the uniqueness is going to hold in some uniform area. So this, yeah, this uniqueness statement has these two conditions, or these three conditions. It's actually a 0 that comes from, you know, the choice of complement to the kernel, and it's in this, you know, delta neighborhood. But then once you have that nearby solution, it actually is even closer. All right. So now we're going to need to actually make that. So let's see. Recap here. So U plus minus actually parameterized Floer trajectories. Let me see. D bar JH is actually DS plus J dt minus XH. And assuming we've proven exponential decay for these Floer trajectories, so I could brutally write this as the S derivative of U plus minus being bounded by some constant e to the minus delta norm S. You might expect this, you know, to only hold on, you know, on the ends, but if it holds on the ends, then, you know, I can just make it hold in, you know, some compact set by just choosing constant pretty big. So, right, an exponential decay here, obviously, if I want decay, I'd better have delta bigger than 0. So So this says that in S direction, the U plus minuses don't change a whole lot anymore. That also implies that then the eta plus minus will have to be small, because at infinity it's 0. And so if you integrate the exponential map, you still get an exponential map. Okay, so that's just the setting of Floer trajectories. Now I want to say, they are cut out transversely and they're isolated. So transverse means that some linearized operator is surjective. Isolated means that the index 1 right, and then mod R, they are isolated. But index 1 means they actually have a kernel. Right? The kernel has to come from the action of R, of the shift. That means the kernel is simply spanned by the S derivatives of U plus minus. Okay. So the real form here is not that important, but for full disclosure, let me get that on. So the linearized operator has a form C going to, well, Cauchy-Riemann operator. Now a linear Cauchy-Riemann operator, because it's J of U, nabla T C, plus a 0th order term that comes on the one hand from varying J in C direction. And on the other hand, there's also the H term. So there's the XH here is the J gradient of H, so this becomes this derivative of the gradient. So, right, this is linear in Xi, that's linear in derivatives of Xi. All right. Good. Right. And, well, maybe since Nate said adjoint, and I just have this here, oops, this guy needs to go here. Right, so if I strictly speaking took the adjoint of these guys, I should think of something that maps L P star to the dual space of W1 P. But that's maybe spaces I don't really want to think about, so I'm going to take the dense subsets W2P, and then I'm going to see that this then maps to the subset W1P in here. Simply because if I, calculate symbolically the adjoint, that the linear part wants to be symmetric. So if I take the right norm or the right metric, it's actually going to be symmetric. So it's going to be exactly the same. And in the first part, there's just some flipping of signs. So it's going to be minus nabla S plus J nabla T. And then plus the same thing. It's actually equal. The reason that we like that is that now D star, right, is something like ds plus J times ds minus J. So this is equal to if you multiply it out, ds squared plus dt squared plus lower order. So we can use that to get nice estimates. And the other reason that we like that is that just sort of in functional analysis, the image of D star, right, is usually a complement to the kernel of D. And that's exactly what we need algebraically. Right, so algebraically it makes sense, and analytically it makes sense because we have this expression here and the Laplacian in the picture. Okay, so now, so this is the function which we want to apply Newton iteration to, and I'd like that to also be a map from W1P to LP. So I'm going to take my zeta. Right, and as advertised, I'm just going to take d bar of x of the preglued one on zeta. Now, the problem is that this is not in that space here, right? So these are tangent vectors to, this map. So I have to sort of move it back to this one fixed Banach space. So there's going to be some parallel transport happening. And there's unique lines just from the exponential map. The reason I need to do this is because I would like this to be a Banach space X and this to be a Banach space Y. And like I want to use my Newton iteration on the same spaces. Well, I want to use them on a Banach space. I cannot have this be a fibration over X. Right? And if I didn't do this parallel transport, then this would lie in a Banach space that varies with zeta. So it would be a fibration. And then, of course, I could always translate a fibration by a local trivialization. But then I have to keep track of the constants that come from that local trivialization. And so I've pushed that into the setup. Yeehaw. Good. So those are the ones that we're content with. Well, and obviously, like all good things, I'm not actually really going to prove everything, right? So here's the claims that are some estimates. So let's see. So first of all, A says that I have an almost solution. And A is true, right? Because the only places where D bar is non-zero is at these interpolation points, right? Except for having to look at D bar JH of X gamma of some beta times eta plus minus, right? But, right, I argued, well, so the exponential decay I argued gave us etas. I didn't say what norm, and by elliptic bootstrapping you can get whatever norm you want. These will be small. well, right. These will be small if I haven't shifted them, and that's exactly where it's important that there's a shift in this construction. Right, so the eta plus minus is actually at some s plus or minus r. And so that's going to give me things, yeah, being controlled by this exponential map. So that's what that is. B says that there is a right inverse. And essentially you can construct the right inverse from the adjoint operator. And that is the one that's actually proven in the Salomon lecture notes. So that's really the key, having a right inverse with. So also key is here that this claim holds with the same constant for all R. Sufficiently large R. So that's the key thing here, that this constant will not depend on the gluing parameter. And C looks like a linear approximation of my map, and this estimate here is, well, it's called quadratic estimate. And what it in particular says is that there actually is a derivative, and that derivative is C1. So because you can integrate this up. So the most useful form of this then says that the differentials vary continuously. And that's here. Same C2 theta. And these are W1. Right, and again, the sort of modulus of continuity, the C2, does not depend on the gluing parameter. So now that's a whole bunch of the key estimates here. And well, how do you prove that? You just write it down. It's like nothing is terribly bad here. These are differential operators. They want to be differentiable. The only thing that could screw things up is this time shift. But the good thing is here the shift parameter R is fixed. So that non-differentiability doesn't get us.
And is there any philosophical reason for why C0, C1, C2 do not depend on R?
Yeah. Well, all of this is kind of trivially true at R equal to infinity. Just hard to say. At the broken one. The broken one is holomorphic, so this is 0. The broken one is transverse, so you have right inverses. And at the broken one, right. And the derivative at the broken one should exist. So that's non-trivial. And then, nearby that should just extend by everything being somewhat, differentiable.
I see.
So that's why philosophically, subjectivity is an open condition. That's that's this transversality here. So, good. So let's see that we can actually get this to work out now. So this is again the Newton iteration written out, with all the settings that we have. So now there's sort of this one thing is we'd like to do it for all R at the same time. So we're going to look at our d-bar operator in this space of sections. We're going to take some little delta ball that's always in there so that the exponential map is defined, for example. Then let's see. Q, the right inverse, that was my constant C1 from the first slide. So, and C prime gives me this estimate here, but with, some constant. So the constant from C prime would be C2 norm zeta, and we would like that to be less or equal to 1 over 2c. And well, I only need that on a small ball, so this here I can replace by delta. But that's still not so good, right? Because I want, how do I know that C2 times delta is less or equal to that? So this just means I have to pick delta small, right? And that's a uniform constant. But now the bad thing is that this delta appears again as in this smallness. I had the smallness in some terms of some exponential map. So what I'd like here is this smallness e to the minus delta r to be less than this delta over 4c, which is, if I've done my algebra correctly, 1 over 8 c1 squared c2 c0. So, right, now there's one more, right, so this is again an inequality. You see that c0, c1, c2 are all important. Oh, wait, I've divided by c0, right? But I have one more element to play with, that's this r, right? So I can get this now small enough by taking r large. That's the R1 for which this is satisfied. So for large enough gluing parameters, I'm going to be in the situation of the Newton iteration, and then I'm going to find my unique solutions, which will be small, and in fact have this better estimate. So, hooray! This now gives us the gluing map. Right? But at least I've defined the gluing map at or near a single broken trajectory. Oops. So that's the broken trajectory. Gluing parameter r is going to be, well, almost the exponent, almost the pre-glued map, but I've added the correction term that I got from the Newton iteration. So, good. So, to do is then all these, injectivity and surjectivity. And I guess I will do that on Monday, just so you get the basic ideas once.